So we talked about the genuine G-equivariant stable homotopy category. So this was defined as the category of G-spectra with the stable equivalences formally inverted. So this is that's a triangulated category. And of course, as you all know, tensor triangulated is structure, not a property, but I explained where the structure comes from and how it arises. So the shift functor comes from the pointwise suspension, pointwise smashing with S1 on the level of orthogonal spectra. The distinguished triangles come from co-fiber sequences at the one categorical level of spectra. The tensor product comes from the smash product on the one categorical level, which is the Dieck-type convolution product, and you have to work a little bit to show that it drives, data drives down there. So then I explained that the spectra, the suspension spectra of all the orbits, V mod H plus for H running over all subgroups of G, or one in each conjugacy class would be enough. So these are a set of compact weak generators. In particular, the category is compactly generated. And I showed that compact objects are the same as, I didn't show it, but I said that compact objects are dualizable objects. And I have to correct a small mistake. So last time I claimed that a general compact or dualizable object is always, you take a finite GCW complex, you take its suspension spectrum, you desuspend, and then you take a retract. But to desuspend, you have to allow by representations. I sort of claimed you only integer desuspensions, and not that would have desuspensions, right? And that would be okay. So, okay, then I talked, in particular, one important feature of which this was a corollary, and this I will need again today, was this natural isomorphism, where I even gave the isomorphism by specifying the universal element between the H homotopy groups of an orthogonal G spectrum X and morphisms in the stable homotopy category from sigma infinity plus G mod H into X. So I even pinned down the universal element that you have to evaluate on. So this will come up again today, and you know that was this compact generation was a relatively formal consequence. And then there were two fixed point functors, genuine and geometric fixed points. So these are two functors, one I denoted by Fg, the other by phi g, which go from the G-equivariant stable homotopy category to the non-equivariant stable homotopy category. And the collection of functors Fh for H subgroups of G and the collection of functors phi H subgroups of G each separately, you know, this family of functors and this family of functors, each of them jointly detect equivalences. So also in the stable context, you can sort of say a matrix is an equivariant equivalence if and only if it's an equivalent on fixed points for all subgroups. You just have to decide which kinds of fixed points you want, and that will depend on the particular problem. Sometimes this is more convenient and sometimes this. They have different features. Both of them are lax symmetric monoidal. This is even strong symmetric monoidal. This commutes with suspension spectrum in the sense that if you apply it to a suspension spectrum, you get the suspension spectrum of the fixed points. This has sort of more interesting, tends to have more interesting homotopy groups. Okay, so now today I wanted to talk about two topics, and let's see how far we get in the remaining 55 minutes. One would be the change of groups. What happens if you have a subgroup and you restrict? And then I want to talk about transfers. I already mentioned that the equivariant homotopy groups really are a McLean functor. These two are a little bit related. So let me first talk about change of groups. So for this, we again have a subgroup, H of G, as we've considered many times, and then let's see what we know about the restriction functor, which I call, well, the restriction from G to H. It goes from orthogonal G spectra to orthogonal H spectra. So first of all, it is obviously a functor between these two categories, because one was just a functor from some Higginson category to G spaces, and you can restrict, so it goes to H spaces. But of course, secretly, we will always want to evaluate the representations of the two groups, and then you have to be a little bit careful. Once you stick in a representation, but I guess it also restricts, you can restrict the G representation. So for example, if I do the restriction of an orthogonal G spectrum at a G representation, this will even be equal to the restriction of the orthogonal spectrum evaluated at the restricted representation. So this all works out. So x and v both have actions of g. I can either take the diagonal action and then restrict, or restrict and then take the diagonal action. So the same thing. Okay, then the next thing is that this has lots of wonderful properties. So this restriction functor, well, it preserves stable equivalences. Tautologically, because we said something is a stable equivalence if something happens for all subgroups. But of course, every subgroup of H is also a subgroup of G, so we're just testing fewer equivalences. So it preserves stable equivalences, it preserves smashing with S1, because that's just done level-wise, and S1 has the trivial action anyhow. It preserves co-fiber sequences. It preserves because those don't really, the actions were just dragged along in the co-fiber sequence. It preserves the smash product, because the equivariant smash product is just the smash product of the orthogonal spectrum with diagonal actions, and that's also just compatible with restricting to subgroups. And this all immediately implies that it derives to a very nice functor on the level of homotopy categories. Well, you don't even have to derive. It preserves all equivalences, so it descends. So this becomes a strong symmetric monoidal exact functor. Okay, so it preserves all the structure that we have, moreover, and it preserves infinite sums and infinite products. Infinite sums, I mean, on the pointed level, it also preserves sums and products. They are just pointwise with the actions carried along. Co-products in the one category of orthogonal G-spectra, wedges, always represent the products, the co-products in the triangulated category. For products, there's a slight issue in that infinite products you have to sort of derive. Finite products are also homotopic with another infinite product, but in the end it works out. Okay, so whenever we have such situations with restricted group action, we're often also interested in going back from the subgroup to the bigger group, and there's often two ways, and so it's here. You can sort of do a left adjoint and a right adjoint, and that may be called induction and co-induction. That's what the higher problem. So let's look at the functors. So restriction has both adjoints. So one of them I want to denote G, and then the semi-direct product symbol XH, which I use for the left adjoint in a pointed context, which this is. So I guess I wanted to call H spectrum Y. So you take the group G, you add a disjoint base point, then you smash with Y. So that's the reduced version of the product, and then you make this identification that GH smash Y you declare equivalent to G smash HY, well, for all G and G, H and H, Y and Y. So this is left adjoint, so this is maybe induction. And again, by the way we defined our objects, they were just functors to G spaces, so I just, post-compose level-wise, I just do this level-wise. If I have an orthogonal H spectrum, that's a functor from some category to H spaces, I just apply this point-wise. That's a continuous functor, and so I immediately get a functor from H spectra to G spectra. There's nothing much to say about. In particular, we can also do the same thing with the other adjoints. Let me call this co-induction. So that's just applying, taking maps from H equivariant maps from G into Y, and this comes with the conjugation, with the action of, so we're taking left H equivariant maps, and on this we still have a left action of G coming from the right action in the source. So G times a map evaluated at some gamma is just F at gamma times G. And again, this is the right adjoint on the level of G spaces and H spaces, and we just do it pointwise to spectra, and it becomes an adjoint again. Okay, so the next important thing is that because we're in a pointed context, there's a natural map relating the two. There's a natural morphism, which I want to call psi, from the left adjoint applied to some H spectrum Y, so Y is an orthogonal H spectrum, to the right adjoint. And to describe it, so this is going to be a G equivariant map. It goes into a right adjoint, so to describe it, I might equivalently give you an H equivariant map only into the Y. So this is adjoint to the H map the H equivariant map from G for Y induced from H to G to Y, which is the projection to the preferred coset, essentially. So I'll give you a formula for this in a second. So this is the projection to the preferred coset EH. You know, after all, if H has index M in G, then the underlying spectrum of this is just an M-fold wedge of copies of Y, and those wedges are indexed by the cosets, and there's a particular one, and we basically want to project to them. So we do this, and element G smash Y, we send this to G acting on Y, if that makes sense, if G is in H. So we start with only an H spectrum, and otherwise we send it to the base point. And this is of course not a G equivariant map. Well, we didn't even have a G actually here. It's only an H equivariant map. And then we use this is right adjoint. And if you want, I'm not going to write down the formula for this, but it's just the adjoint of this. Okay, so this is a natural morphism. Again, this is really something about, I guess, base G and H sets and then base G and H spaces, and we're just doing it level-wise to our spectrum. Okay, here comes being excited about these things. The functors G blank H and maps H equivariant G blank, which go from orthogonal H spectra to orthogonal G spectra, preserve stable equivalences. So they descend to functors on the homotopy categories, which are then automatically adjoint to the restriction again. And psi is a stable equivalence for all Y orthogonal H spectra. So in other words, on the one categorical level, there's this morphism, which is a natural stable equivalence. Both functors are fully homotopical, so when we go to the derived category, it will become a natural isomorphism. So corollary, the restriction functor GH from orthogonal G spectra to orthogonal H spectra has both adjoints, and they are naturally isomorphic. And these are naturally isomorphic. So, you know, if you come from algebra, modular representation theory, this is something you're perfectly used to. You know, if you take G modules in abelian groups or KG modules or something like this, as long as G is finite, that's the same is true. And it's much, much easier to prove in that context. The sort of surprise, and it's of course false for G spaces. For G spaces, you have both adjoints, but they're far, you have this map. And this map is far from being equivalence, and there's also no other equivalence. So this is really a stable phenomenon. It's also something that depends on the fact that we inverted all the representation series. So sometimes people call this phenomenon the Wirthmüller isomorphism because it is closely related to the theorem that Wirthmüller, the student of Dieck, actually proved, although what he proved wasn't really this. It was something that amounts in content pretty much to this. And he proved it even for compact Lie groups, where the statement is a little bit more complicated because for compact Lie groups you have to build in a twist in the adjoint. And it's not literally true in this sense. You have to modify the statement. Okay, I think this is a key result, and I actually want to give you proof of that. And here's how it goes. So we're going to analyze the geometric fixed points of the two sides. And we have to do this for every subgroup, and then we're going to see that if I take k geometric fixed points, when k is some other subgroup, not just H necessarily, we're getting an equivalence. So let's do this. So let k be another subgroup of G. Okay. So then we have this tautological decomposition. If you look G, if you consider G with the left action by k and the right action by H by translation, it tautologically decomposes into double cosets. So this is the disjoint union over all, how do I want to write this? Overall K, G, H in the set of double cosets K mod G mod H of K, G, H. So I'm just decomposing this thing into orbits under the action of G cross K. So this is SKH bisets. Now I want to calculate the K geometric fixed points of the induced spectrum. I take an H spectrum, I deduce it up to G. So For this, of course, since I'm going to take k fixed points, I'm secretly restricting from G to k, so whenever this decomposes with k and h actions, I get a decomposition on this level. So this is isomorphic to the k geometric fixed points of the wedge over our double cosets, kgh, and then kgh plus smash over h with y. But then this can be rewritten. That's a pure right argument that you've probably seen if you ever had anything to do with double cosine formulas. But I need some more space first. So I'm not going to rewrite each individual summand, and I'm going to use that geometric fixed points, which if you go back as to what it was, you were taking fixed points at every level, so that commutes with wedges. With all sorts of constructions, in particular with wedges. So I'm going to put the wedge outside of the geometric fixed points, and I'm going to rewrite each of the summands a little bit. Okay, so let me put the wedge out over all double cosets, kgh of the k geometric fixed points, and then I can rewrite the thing in between as a different deduction. I first have to take this h spectrum y, I have to change its action along the conjugation map. I'm going to tell you in a second what that is. Then I have something on which k intersected the conjugate subgroup acts, and I induce up. And this is just something about k and g sets, about finite sets with group actions. And what is this CG? That's a conjugation homomorphism. So I want to consider this as a morphism from k intersected gh to h, which just sends a gamma to g inverse gamma g. It's a conjugation. Applying this to an orthogonal h spectrum again means restricting scalars at every level. In order to have a group homomorphism, I can post-compose my orthogonal spectrum with the restriction of scalars functor, and I can change the group actions this way. And you know, this is no magic, this is just something about G sets. Okay, and now we observe that here we had something with an action of this subgroup, we induce up, and then if you remember what geometric fixed points were, at every level we were taking fixed points. But that means that whenever this group is actually strictly smaller than that group, it's not going to have any fixed points other than the base points. So whenever this is strictly smaller than that, this is going to be the trivial spectrum, which just has the point. So those summands drop out, and what remains are only the summands in the double coset space, only the summands kgh and k mod g mod h, such that, well, when is this the same? That's exactly the case when k is contained in this group. So that's such that k is contained in gh. And then these two groups are the same, so there's no inducing up happening, so we're just taking k geometric fixed points, so of phi k cg upper star of y. So this was the analysis of the k fixed points of the left-hand side, and we can immediately see, you know, this is a conjugation homomorphism, so that means we're restricting to a subgroup and we're changing group actions by an isomorphism, and those of course preserve stable equivalences. So restricting to subgroups preserves stable equivalences, and you know, changing things by an isomorphism obviously also does. Phi k fixed points preserve stable equivalences. That's something I didn't prove, but I already used last time. And you know, infinites and wedges preserve equivalences also. So we can immediately see that this functor takes equivalences to equivalences. So phi k after g inducing up takes h equivalences, h stable equivalences, I should say, to non-equivariant equivalences. And since this is true for every subgroup K of G, we've shown that stable equivalences go to stable equivalences. So we've shown that the functor G inducing up preserves stable equivalences. This was one statement. So now I could show with a very similar argument also the right adjoint preserves stable equivalences. But since we want to show the map is an equivalence anyhow, I'm going to do that, and then we know also that the other one preserves stable equivalences because it's always stable equivalent to this. So I'm now just going to do the analogous kind of dual analysis of the geometric fixed points of the right adjoint. Some things are going to be very similar, and we're going to see we end up with the same number of summands. Well, in one case it's going to be wedge, in the other case product. Yeah, and then we can see we get the same answer, but for this we will need one lemma. So now I want to do the same analysis like for the right adjoint, and for this I need a lemma. So for L subgroup in K, so the K will be soon the one that we take geometric fixed points with respect to, and for some spectrum that has an action of L, then we have the following thing. If I take K geometric fixed points of the right induced thing, of the co-induced thing, then two things can happen. So then this is either just the L geometric fixed points of that if they're the same. This is a triviality, because then no inducing up happens and L and K are the same, and otherwise it's contractible. L is less than K. And this is slightly less obvious than in the left adjoint, but it's also simple. So let me prove this for you. So the first statement is clear. If K is equal L, no injection, and then that's the same. So the real thing is the second statement. What if this is not the same as K? Let's expand the definition of this at some level. So what is the K geometric fixed points of the right induced spectrum at R to the n? Because I want to show some non-equivariant spectrum is trivial, and what I will show is when I evaluate this at copies of Rn and then stabilize, I'm going to stabilize over null homotopic maps. So let's expand what this is. So I just have to plug in all the definition, and then we get out that this is, at first take n equivariant maps from K into the value of this, but at the regular representation and then fixed points, because the definition of geometric fixed points involves evaluating the equivariant spectrum as something times the regular representation and then taking fixed points. So I have to take this as at R to the n tensor rho K at rho K, because I'm taking K geometric fixed points, and then I have to take K fixed points everywhere outside. So, but then of course if I first co-induce and then take K fixed points, that's the same as taking L fixed points of the thing that's inside. So that's the same as evaluating Z at n times the regular representation for K, that's important, and then taking L fixed points. And if you don't pay attention to the structure maps, you might not see why this is a problem. But this is an issue because if L is strictly smaller than K, this is growing much larger than it's supposed to, and this is why the structure maps will be null homotopic. So more precisely, for the structure maps, and now it's slightly unfortunate that I actually didn't explicitly give them to you, but there was basically only one choice. So the structure map is going to go from S1 smash this value, which is Z evaluated at n times rho K, L fixed points, going to the next one, which would be Z evaluated at 1 plus n times rho K, but only L fixed points. And if you have worked out or looked up what the structure maps are, you will see that this S1 really comes up as the regular representation K fixed points, which are one-dimensional and which you have to sort of identify with the standard S1. And if you believe that, you will see that this will factor, because we're taking L fixed points through the regular representation for K and then L fixed points smash Z n times rho KL. And then the second one would be you pull the fixed points out of the smash and you use the structure map in. Okay, but now if L is strictly less than K, then this is a sphere of a strictly larger dimension. And then in that situation, this is what we're assuming here, this map that we're smashing with is null homotopic. So we have a non-equivariant spectrum in which the structure maps are null homotopic maps, and then of course the stable homotopy groups are zero, and that spectrum is zero. So that's the reason why on the right hand side, it's a slightly more complicated argument than for the left adjoint, where it would just be the trivial spectrum on the point, a point everywhere. Here it's not, but the structure maps, you know, the entries grow too fast. The structure maps have to be null homotopic. Okay. So now we are ready to identify the fixed points on the right hand side. But I need more space again. Okay, so let's now look at with these two subgroups. H is the one we are co-inducing from, and K is another one, and we take K fixed points of the co-induced spectrum. Okay, so the first thing is again that we use the tautological decomposition of G into double cosets. So this is the product tautologically over all double cosets, and then I take maps H equivariant only from this one double coset into Y. Geometric fixed points are fixed points pointwise. They can be used with products also, so I can pull the product outside. So that's the product over all double cosets of phi k. And then I'm going to do the dual of the rewriting that I did up there in the left adjoint, and the dual sort of form makes this come out H equivariant maps from K cross over using the conjugation with KG smash H into Y. So this means I take K times H and I divide out the action of this subgroup, which acts via the inclusion here and via the conjugation here. And then again, I can adjoint this. So this becomes the product of KGH, geometric fixed points. And then again, because I'm first co-inducing something, this would just be the same on the one categorical level as K intersected GH equivariant maps from KG into the restriction from H to KG into HY. So in all of these rewritings, there is no homotopy theory happening. This is just basically G-sets manipulations. And now I'm in a similar situation. I take something with an action of this smaller group, I co-induce it, and then I take, sorry, this would have been geometric fixed points, the conjugated one, because secretly I'm conjugating somewhere. So I'm co-inducing and then taking geometric fixed points. And I just had this little lemma that unless these two groups are the same, that will be contractible. So I'm going to drop those summations, and I'm going to get the product over those double cosets, KGH and K mod G mod H. And again, the same condition comes up. They have to be the same. So this group has to be the same as this group, and that happens if and only if KG is contained in H, which is of course the same condition as K being contained in GH, where the G is on the other side. So that's the same condition, the same double cosets come up, and then we have phi KG of Y. And now you have to trust me that the map psi that I used identifies that each of those summands with the same summand here via a conjugation map, because in one case I have phi fixed points, but I have conjugated the action, and here it's the other way around. So those are isomorphic things. All the other summands are either trivial or contractible, so that they don't matter. And now I'm in the statement that I have a bunch of non-equivariant spectra, of which in one case I take the wedge, and in one case I take the product. So we already know, we've already used that non-equivariant wedges and products are the same. So that map is an equivalence on K geometric fixed points. And because this was true for every K, you know that it's an equivariant equivalence. So this was essentially a proof of what's sometimes called the Wirthmüller isomorphism. Well, I mean, it was a proof, but there's one subtlety with this. And you know, if you set things up the way I did it, if you define equivalences via equivariant homotopy groups, then the fact that they're also detected by geometric fixed points requires proof. And one of the standard proofs of that uses implicitly the Wirthmüller isomorphism. So you have to come up, you either have to change your definition of an equivariant equivalence, you know, why not define it as a map that's an equivalence on all geometric fixed points right away? Then you don't have to prove that, and then this is a valid proof. Or you have to prove the fact that smashing with E tilde P preserves equivariant equivalences, or you have to prove that without reference to the Wirthmüller isomorphism. It is possible, but it's not the standard way it's done. So this can be made into an actual proof, this argument. Okay. You can also argue via genuine fixed points, but I think that's a little bit more complicated. This is sort of a simpler way. Okay, so any questions about this?
So
yes.
So the proof that I've seen of the Wirthmüller isomorphism before is very geometric. And so I guess the geometry here is hidden in the fact that it's the geometric fixed points.
No, you can. I think that Mandel may have a more direct argument that.
So you can avoid this.
I think you can prove that also. Yeah. I mean, the geometry really becomes necessary when you want compact E groups, because then there's this twist by the representation of the tangent representation of H, and then even to construct the analog of the map psi, you need tubular neighborhoods and so on. So for finite groups, I think there isn't all that much geometry involved.
So why would the proof differ if you use genuine fixed points? But what would be the thing that becomes more difficult?
I mean, I don't know. I mean, you can set true things, you can prove in many different ways. I mean, I would usually first construct the Wirthmüller isomorphism, showing that the equivariant homotopy, the G-equivariant homotopy groups of the induced up spectrum are isomorphic to the H-equivariant homotopy groups of the thing. That's what I would usually do first. And that's also for finite groups. It's an explicit argument, but the one that I know use such things as that coproducts and products of G spaces, if you stable enough, are in a range, have equivalent fixed points and so on. That's, I don't know, I mean, there's many different ways of setting things up. Okay, anything else?
So what is actually the statement for compact Lie groups?
Compact Lie groups, the statement is that G, so let's see, on which side do I put this here? I think on the other side. Maybe I hope I'm not putting it on the wrong side. Map G, map H. Or which way? John's going to correct me if I'm wrong. Do I have to put it here or on the other side? I always have to sit. That looks good, right? So what is L? So L is the tangent space at the H at the preferred coset of G mod H. So if we're in the compact Lie case, and H doesn't happen to be a finite index subgroup, but maybe one of strictly smaller dimension, then this is a manifold, a nice smooth manifold, but of positive dimension. So we take the tangent space at this special point H, or to emphasize that I want to look at it as a coset, I write EH. This is a vector space, first of all, of the difference of the dimensions of G minus H. So this is a real vector space, and the addition of L is the difference of the dimensions of G and the dimension of H. In particular, if there were like the same dimension, we would just have a point and all this discussion would be unnecessary. It's really only necessary if this has strictly smaller dimension. But this is not just a naked vector space. So on this manifold, of course, G acts by translation. This point is not G fixed, unless H happens to be equal to G, but that's not the interesting case, but it's H fixed. The special coset is H fixed, and that means that you get an induced linear H action on this tangent space. So this comes to us with an action of H, and that's the action I'm using here. So I take this H spectrum, I smash it. So this is sort of a suspension by the difference of the dimensions, but in a twisted way. In interesting situations, for example, if H is a normal subgroup of G, it might be that this action is actually trivial, and then that's just a dimension shift. So then it's saying the equivariant homotopy groups are the same up to a dimension shift. But in general, this can be a twisted dimension shift, a representation graded dimension shift, because, you know, very often this action is not the trivial action. And then in some homology theories, maybe they have, you know, from isomorphisms you can undo the twist, but in generic homology theory, you won't be able to undo the twist. Okay, so that was what the statement in general is. Anything else? Okay, so then let me talk a little bit about the Mackey functor structure. So, because this already came up and I think it's an important feature. So this is the natural structure that you have on the equivariant homotopy groups, not just for G, but also for all the subgroups. And now I'm here to go, here's the switch. Okay, so suppose the transfer, we will have restriction maps. I'm going to have natural restriction maps, which go from the G equivariant homotopy groups of X to the H equivariant homotopy groups of X. I'm going to have conjugation maps, CG, maybe I sometimes want to call them G lower star, which go from the H equivariant homotopy groups of X to the H conjugated. Which side do I have to conjugate? On this side. H conjugate homotopy group of X, and I'm going to have transfer maps H to G from H equivariant homotopy group X of X to the G equivariant homotopy groups of X, and all of this I'm going to have for X's in orthogonal G spectrum and for H subgroups of G. And I'm gonna have this a little bit more general. I could have an H and then a K inside an H, and I would have this by just restricting to an H spectrum and doing it there. And altogether, this data will form a Mackey functor, and I want to explain a little bit what this comes from. So you can do all of this in an abstract fashion, using the representability of equivariant homotopy groups, or in a more concrete fashion, where you actually pick representatives, do some constructions to them, and then have representatives for what the operation is supposed to do. And I will give you a little bit of both. If I have enough time, I will maybe sketch both perspectives. A lot of time at some point. So all of these are supposed to be natural transformations on G-spectra from pi equivariant for some group to pi equivariant for some other group. And I told you that the equivariant homotopy groups are represented. So there's this natural isomorphism pi h of x, the same as morphisms in the G equivariant stable homotopy category from sigma infinity plus G1 hx. And that means if I'm interested in natural transformations of functors on the stable homotopy category, two sets, say, between two such functors, then the unit dilemma will tell us what they are. Well, it gives us a different answer for them at least. So natural transformations from pi 0 h equivariant to pi 0 g equivariant, because the source functors representable will be naturally isomorphic to the k equivariant homotopy groups of sigma infinity plus g mod h, and that will also be naturally isomorphic to morphisms in the G equivariant stable homotopy category between the representing objects, but now they come in the other order. So sigma infinity plus g mod h. And now this is one way how you could immediately calculate all natural operations if you knew what this abelian group was, and the Tom-Dieck splitting is a possibility to tell you what this group is. So this is one approach. If you have the Tom-Dieck splitting available, you sort of calculate this. If you don't only remember that Tom-Dieck provided some isomorphism, but you remember which map is an isomorphism, you can even identify like tensors, restrictions, and conjugations. It's always better to know which map is an isomorphism than just to know things are isomorphic. Okay, but I want to not do the full calculation. I just want to give you some idea of where you get the key operations from. And then, of course, you have some operations, you can take linear combinations of those, you can compose them and so on, but this will generate all operations. So, but first of all, in particular, we see that whenever we have an unstable G map from just G mod K to G mod H, then we're going to get some operation. So, every G map from F from G mod K to G mod H yields sigma infinity plus F from sigma infinity plus G mod K to sigma infinity plus G mod H, and this yields an operation that I want to call F upper star from pi 0 h of x to pi 0 k of x. And the restriction and the conjugation actions come from this. So for example, if I have k contained in H, contained in G, then I can just look at the projection, G mod K. So if K is a smaller group, then I can identify more things. I can look at the natural projection onto this, and this induces a restriction homomorphism. Restriction from H to K from pi 0 h of x to pi 0 k of x. But this map can also be given explicitly. So if I have a class in that group, so that would be an equivariant map from n times the regular representation to the value at n times the regular representation of h, and it would be an h equivariant map. And if I want to restrict that from h to k, I just restrict the representative. That's all I do. Well, almost. So I take the restriction of the representative from h to k. So this is going to be a map from the restriction of n times rho h to x at the restriction, well, I guess the restriction outside of x evaluated at n times the regular representation of OH. Now, the issue is that if I restrict the regular representation of k to h, it's not exactly the regular representation of h. It's also not exactly a multiple of that. But if I choose coset representatives, and it's not going to depend on that choice, then the underlying k representation of the regular representation is just m times the regular representation, and m is the number of this index in there. So I can identify this if I choose coset representatives with k n times the regular representation of k, and this would be x evaluated, well, formally the restriction of x evaluated at k times n times the regular representation of k. So here I have the restriction of f, and k would be the index of k and h. And so that's a k equivariant map. So the restriction homomorphism can abstractly be defined by precomposing with a projection, but concretely it's really just restricting the actions. Conjugation is very similar. So conjugation comes from the G map from G modulo the conjugate group to G modulo H, which sends the coset of gamma for the conjugate subgroup to the coset of gamma G times H, and this induces the conjugation homomorphism. I guess I wanted to write it G lower star from pi 0 H equivariant of X to pi 0 conjugate subgroup H equivariant of X. So abstractly it comes from the fact that you have an unstable G map, but you can also take a representative, apply the conjugation homomorphism to the representative and identify the regular representation restricted along conjugation with itself via multiplication by the element G. So that, in some sense, you can also take the representative and restrict it, and that would be a concrete description of that matrix. Okay, and then maybe the most interesting things of all of these is the transfer, and I hope I have like 5 minutes left, because that does not arise from an unstable map, so that's really a generally stable feature. I mean, this is maybe related to the fact that unstably, the homotopy groups for all the subgroups would form a coefficient system, not a Mackey functor, and stably they form a Mackey functor.
Stefan, you have 20 minutes, right?
No, I started at 2:15.
No, we started at 11.
Oh, it started at 11. Ah! No, this is happens if you. Yeah, because I always start at 2:15. Ah.
So you can write, you know.
Okay. Can actually write lecture, please. Gosh, you know, every day I started at 2:15, so it's not. Okay, this is great. Can I get coffee? Okay, so just the transfer. 15 minutes is enough. That's a whole new world. Okay, so how do we get the transfer? So again, we have nested subgroups K in H in G, and the transfer from K to H will be a natural operation from pi 0 K equivariant of X to pi 0 H equivariant of X, and I'm going to give you 2 perspectives on it, and I think one of them was already mentioned at least briefly in the first exercise session, so maybe there's going to be a little bit of duplication here. So, but the first observation is if you wanted to apply that strategy, it sort of wouldn't work. So it's a little bit different because there is no G map. So at least if K is different from H, if they happen to be the same, there is, from G modulo the larger group to G modulo the smaller group. So this doesn't exist. And so you cannot use this construction up there, so you have to do something different. But there is a stable map. Well, stable just means in the genuine equivariant homotopy category between the suspension spectra from sigma infinity plus G mod H to sigma infinity plus G mod K. And here's how you can get it, and I'm going to give you 2 different perspectives on that map. So one will be abstract, it will use the Wirthmüller isomorphism to define it, and this will make some people happy, and the other one will be more concrete, it will use a Conjugation construction. And they will be the same, they will be the same maps in the end. So one construction is as follows, so namely, so this is induced from an H spectrum, namely from H mod H induced up to G. This is also induced from an H spectrum because K lies in between, namely from H mod K. So when I'm going to give you really a map there, and then I'm going to apply the induction functor to it. So I'm going to give you really a map from sigma infinity plus H mod H to sigma infinity plus H mod K eventually. So how does this map go? So this is the sphere spectrum, the H equivariant sphere spectrum, because H mod H is the point and its suspension spectrum is the sphere spectrum. And here I can take a diagonal map into the K equivariant maps from H into the sphere spectrum. So, you know, this is a product of copies of the sphere spectrum, as many factors as the index of K in H has. And if I take, you know, really the diagonal, then in each factor, it's going to be an equivariant map. And this diagonal I couldn't map into the, you know, into the wedge. It's really a diagonal. The diagonal doesn't lie in the wedge unless you have a single factor. But stably, this is not a problem because the map from the wedge to the product is really an indexed wedge and an indexed product. This is a stable equivalence, as I just showed. This is a special instance of this sort of Wirthmüller isomorphism just for the sphere. And then once in the wedge, I can fold or add, or however you want to call this, fold or act. I mean, this is the unit of the adjunction, if you want. So this came from the H spectrum, which I restricted down and then induced up again. Or I could just say this more concretely. I just send H smash X to H times X. I do the action map. That's an H equivalent map. Oh, sorry, no, I wanted to stop here. Okay, this other would have been the transfer in the homotopy groups, but I wanted the other element. No, I wanted to stop here, and this is by shearing isomorphism. This is sigma infinity plus of H mod K. So whenever you have something with an action of the bigger group, you restrict and you induce up again. This is isomorphic to the product with the diagonal action of the thing you already had and the coset by some shearing isomorphism that puts like an inverse in one of the 2 points. Okay, so this gives me, all of these were H equivariant maps. So it gives me an H equivariant map from here to here. I induce up and I get a K equivariant map here. And you know, unstably, this map is not an equivalence. You cannot invert it. So this is a really stable phenomenon. Okay, one comment at this point. Note, maybe I do this later. Okay, so now I wanted to do the more down-to-earth construction via Tom-von-Triagen construction, and here's how that goes. Okay, so we consider the H equivariant embedding from H mod K. So this is an H space, but it's really an H set, finitely many points, as many as the index of K in H is. And I'm going to embed this into the regular representation for H. That's because I'd set up equivariant homotopy groups with multiples of the regular representation. I mean, secretly you could choose your favorite representation to embed it in, that would also work, but I chose to do everything with multiples of the regular representation. Which one do I take? Well, the most obvious one is I take the coset H times capital K to the sum over all K in K, H times K. That's going to be an H equivariant map, and it's going to embed. And if the index is 3, maybe the map looks a little bit like this. So this is a picture when K has index 3 in H, so maybe this is where the preferred coset goes, and this is where H1 K goes, and this is maybe where H2 K goes. And now I'm going to use the Tom-von-Triagen collapse map that gives me a map in the other direction. That means I choose small balls around these points, and I choose them so that the whole thing is, what's the group that acts? H, it's H equivariant. So this ball has the same radius as this ball, so that the H action sort of matches them all up. And then I do the Tom-von-Triagen collapse construction. So Tom-von-Triagen collapse. So what's that? That's going to be a map from the one-point compactification of this representation. So that's a map from rho H, sphere of rho H. And where does it go? Well, I'm going to send everything that's not in the interior of one of these little balls to the base point. Inside of these little balls, I use some scaling function that scales, the interval 0, 1 out to 0 to infinity, so that I can, and that I use to identify ball modulo its boundary with the representation sphere. And then I remember all of them and the way they are permuted. And that's in more closed form. That's really H induced up from K as H. So there's going to be as many small balls as the index of K and H is, and this is a wedge of the same number of copies of the sphere wedged together. So this is basically what you do. If you're outside of these balls, you go to the point at infinity. If you're in one of those balls, you remember the coset in which you are in. That gives you this H, and you sort of stretch out from 0, 1 to 0, infinity.
And subscripts are K.
Subscripts are K. Thank you. So where does this lie? And this whole thing, I mean, usually I draw maps from the left to the right, but here it's because of the collapse, it goes in the other direction. Where does this land? Well, this is exactly an element. It's an H equivariant map. So it lies in pi 0 H of something. And again, via shearing isomorphism, the same one I used before, this is H mod K plus smash S rho H. This was not just a K representation, but an H representation. So I can shear, and this lives in pi 0 H equivariant of sigma infinity plus H mod K. And now I mean, somebody has to check, and of course you can read this up in the literature, but this describes the same element that was abstractly described by this one here, and then it's a personal taste of what you prefer. And now I have a problem, because I thought I had 15 minutes less. I was going so fast that I'm at the end of the material that I've prepared. So either we all have 10 minutes extra for free, or you just ask me some question, and I am going to improvise. I can't do tap dance or something like this. I'll try to do more Equivariant.